Welcome everybody to this webinar from the project OceanICU. This webinar is about the project's task of building decision support tools. And today we have three distinguished speakers presenting different aspects of this task. Dr. Jorn Brueggemann, sorry Jorn if I got that wrong, who's going to be talking about the challenges of building decision support tools with big data. We've got Dr. Patrizio Mariani. I apologize again if I get that one wrong. He's going to talk about machine learning in Earth System Science. And Dr. Marina Tonani, who's a guest speaker today from Mercator Ocean, who will be speaking about the impact and from using the European digital twin of the ocean infrastructures, which is in the backbone here. So quickly, I'm Dr. Conor Delaney from Seascape Belgium, and I'm doing the moderating. So I'm just going to give you a quick housekeeping on all this. The webinar is recorded. Your cameras and microphones have been disabled. You can put your questions in the chat. At the end of the webinar, we will address the questions, and I will redirect them to the suitable person. If we don't get time to deal with the questions, we will deal with them afterwards and share them with answers through the OceanICU website. We have 45 minutes, and during the session, the only people with their camera on will be the speakers. So next slide there, please. So I'll just quickly go on to this slide and just go back, next slide there, Matteo. So we're talking about the role of or the cycle of ocean carbon, and what the project is looking at is trying to understand this, have a better understanding of this, and Jorn will give you much more detail on this. I'm just trying to give you the high altitude view, and we're also looking at decision support tools on building tools that allow people to understand the impacts of human activities such as fishing, dredging, drilling on the ocean carbon cycle. The ocean is a major sink of carbon, and therefore it is extremely important. We go on to the next slide. So Jorn is from Bolding and Brueggemann consultancy firm, and he will go into dive into the details on the various aspects of building decision support system. Patrizio is from the Technical University of Denmark, and will talk about the use of machine learning. And as Marina from Mercator Ocean is the project manager of the European Digital Twin of the Ocean Infrastructure, and she will introduce it to you and give you and explain how this has been an underlying technology for the OceanICU, and is very much a technology that can be used by Horizon projects to service big data problems in the digital twins of the ocean space. So I'll just pass you now on to Jorn and let Jorn take over with his presentation. Thank you.
Great, thank you very much, Conor. Thanks everyone for being here. I'll give a quick flavor of what we're trying to do in terms of building decision support tools in OceanICU. My background is in modeling, mostly ecological modeling in marine systems, sometimes hydrodynamic modeling. Spent some time in various institutes, most recently Plymouth Marine Laboratory, doing that in research, and these days I'm working for a consultancy, as it says here on the slide, as Conor mentioned. So the project, and some people will have seen previous webinars will be up to date on this, but the project is about the biological carbon pump on large scales in general, global scales, sometimes regional scales. And the focus is on resolving a number of new processes and seeing what impact they have on the carbon pump, and at the same time looking at the different human pressures on those processes and on the carbon pump. So we're looking at a number of different pressures, which will come with scenarios right here. And we're looking at a number of new processes listed here. That's what the project is about. And one component of that is that we'll try to work towards delivering tools for decision makers that can help them fit in the biological carbon pump into their decisions, make sure that it features. So the project is large and covers anything from collecting new data, assessing the current state of the carbon cycle, to looking at understanding new processes from abiotic to ecology and human pressure, to modeling and quantifying impacts, to then finally the resources for decision makers and impact on society through stakeholder engagement. Different webinars have talked about different components of this project, and I'm sure new webinars will talk about different components. Today it's about resources for decision makers, so this work package 7 on decision support tools. But before we get there, it's good to take a step back and think about decision making in a marine space, because what's this about, and how can we make sure that biological carbon pump features in decisions? It depends on what the questions are, what the decisions are being made. And we cover a whole range really, because the project looks all across industry to policymakers. We have people in work package 8 on stakeholder engagement that directly talk to these people, and the questions that they ask day to day are broad and cover a whole range of topics, from issuing licenses for mining or other activities, to looking at impacts of fisheries and setting quotas, to deciding which areas should be protected, and the new marine protected areas and the like, and making decisions about commercial activities, from investing in new gears or technologies, or preparing for upcoming change in policy or public opinion. The key thing here is that in general these questions tend to be specific. They are specific to particular regions, to particular time periods, to particular species, to particular gears. They are not so easy to answer with generic tools, and even though we are building tools in this project, it's worthwhile realizing what the landscape is, and realizing that we cannot answer everything with a single generic tool. And what's more, decisions are not built on a little online run in a web browser of a little tool. This is a real example of projects we've worked on, where decision making was about whether or not to build a new nuclear power station in the United Kingdom. Admittedly, that's a large decision being made, but this involves environmental impact assessments over decades and millions of pounds, as it says here. It involves modelers, empiricists, literature, study, field work, modeling. It's not something you can quickly replace with a single automated tool, no matter what you do, and we are fully aware of that. And we're looking here at this power plant. We worked on this for over a year, looking at the impact of the water outflow at a particular point there in the Bristol Channel, as you can see here. That's a lot of outflow. It's like a major river, and we're looking at the heat spot there. That's just one little cog in the entire environmental impact assessment, and it took a year. It's not something you can replace with a single automated tool. So what really are we trying to build here? What are we trying to do? The space for decision making in marine systems is huge. So what we think we can do, we think we can inform perhaps the very first phases of decision making, when you're really starting to explore what you might be doing. We might be able to offer quick tools to assess what a rough change in fisheries, in mining, in carbon emissions would do to particular sites in the ocean, what the impact would be on primary production, on carbon sequestration and the like. But only the very first phases. We are fully aware that in the end many decisions will involve large-scale environmental impact assessments. We can offer something there though, because we will build our tools on a framework that easily scales to the real state-of-the-art environmental impact assessments. We're using the same models. We're making sure we're using everything in the same way. So there is a clear pathway to scale up. But beyond that, decision-making does not happen in a vacuum. It's not a question just for the decision maker. It relies on everyone involved, all stakeholders, being aware of what's going on and realizing what the problem at stake is and how the different parts of the problem hang together and what the causality is. So what we think we can do is we can help stakeholders in general explore and understand how pressures impact the marine carbon cycle and what the different processes in the marine carbon cycle do. And that benefits all, not just decision makers, but also managers, industry, stakeholders, indigenous groups, and in the end, the general public. So that's what we think we can do. Now, OceanICU will produce a range of decision support tools, and that's really tools in the broadest sense. We've delivered the first report, version 1 here, that describes existing resources, pre-existing resources at the start of the project, that includes datasets and tools that could help underpin decisions right now. Then there's a version 2 coming up. We're here today, and we're looking in a year and a half's time or so at a set of interactive tools, process-based tools for multi-stressor simulation and visualization. So we're looking at simulating the impact of stressors and looking at what happens to the carbon cycle. And finally, towards the end of the project, and that's something that Patrizio Mariani will talk about, we're looking towards a machine learning based tool to really explore in more detail what the different scenarios will do. Today we're talking about this version 2, so building interactive tools based on process-based models. Now the benefit we have in this project is that there is a large slice of effort, a large resource there on model development. There's in work package 6 we're building to a generic model framework where we can combine a range of different circulation models from very simple to very complex. And we can combine them through a coupler here with a whole range of biogeochemical components, and in the end also ecosystem components such as fish and fisheries. The key thing there is we have a whole range of models on the left, a whole range of models on the right. We can combine, mix and match them at will and make combinations that we think are feasible. And initially we'll work with lightweight model runs here on the left, lightweight test beds, but there's a clear pathway to scale up to really high resolution production simulations as are being used, for instance, for the Copernicus Marine Service, for the people who are aware of that, and also for IPCC climate assessments. So we're building on a framework, and we're using a framework that really can scale all the way up to the most state-of-the-art circulation simulations and marine ecology simulations. Today we're focusing on test beds, and that is for one key reason is we want to build tools that are quick to run and that really are interactive. People can click buttons, wait perhaps seconds, perhaps a minute, but not more, and get a feeling for what the impact of a process is. So we're not going for the full state-of-the-art three-dimensional simulations that take days, weeks, months perhaps to run, but we're looking at these test beds that I showed you before that are quick to run. And they all make compromises because they're test beds. They want them, in order to run quick, they make a compromise. First, for instance, they look in detail at the vertical, as this Kotter model does, but they don't have any resolution for the horizontal. They look at a single water column. Or they look at the global ocean at pretty coarse resolution, but use pre-calculated physics. Or they have an Earth system model, again at coarse resolution here, with limited match-ups with historical data and historical periods. The key thing here is we're aiming not only for detail in space and time, but we're also aiming for short run times. You can see here that these models, they might take seconds to run or minutes to run, but we're not going beyond that. And today what we are focusing on is this top one, just to be able to show you quick tools, so this water column simulation. For some purposes that might be very informative. For some purposes you would want to have a basin scale or global scale answer and that not be through a water column model. And so we're not there yet. These are the first steps we're taking. So concepts are, we want users to be able to come in and configure a scenario, and set some levers that represent human pressures such as fisheries, such as mining, such as climate change. Then we want to run live simulations here with process-based models, such as the test beds I just mentioned. And we want to look at impacts. So we want to analyze results quickly, visualize them quickly, and we want to be able to do that all in a responsive manner. So we want to present this to a user through a web interface. People can really go through this entire chain in seconds, maybe minutes, but we're really aiming for quick response times here for now. I'll give you a quick demonstration of a proof of concept, the one we've built, and I'll talk a little bit more about what's behind that in a second. So stop sharing this one and share my browser instead. I'm hoping you can see that. This is a OceanICU application running on top of the digital twin of the ocean, and we'll talk more about that in a second. But the concept here is you can look at a map globally, pick any location you like, any location as long as it's marine, click there and models will run directly, immediately. So let's click a site in the North Sea, and then it says in quite a lot of detail at the moment what's going on. It sets up a model, it runs the model, it collects all the information about that site in the meantime, it collects information on water depth, on meteorology, on tides, just to be able to simulate that water column right there. You get predictions of temperature with some satellite data next to it to show how good or bad the model does. You get predictions for chlorophyll, and these are a number of different biogeochemical models. I'll mention a little bit more in a second. And predictions for CO2 flux. This is a prototype. These are not the final metrics we'll show, these are not the final plots we'll show, but you get a feeling for what is happening here and the fact that we can run these models on demand in response to user configuration, really. So this is a reference simulation for a particular recent year, but what we are aiming for, as we said, is we want users to configure scenarios in terms of human pressures. And as a demo for that, we have this lever here for air temperature increase as a placeholder for climate change. And if I increase the air temperature by some degrees, a 2-degree increase there, the models run again in the background. You see the same original model run, but now a dashed line for the scenario. So you get higher water temperatures. These are sea surface temperatures. You see the mean temperature here in the reference simulation, and in the scenario, you see that the water temperature has increased. Not quite by 2 degrees, because the ocean is slower to respond, but with some temperature increase, maybe a degree or so. You can go back to chlorophyll and see the same type of impact, or in fact you can see here that the impact on chlorophyll happens to be very, very small. You can go to CO2 flux and you can see that with that 2 degree increase in temperature, the CO2 flux has decreased from this mean value to that mean value, which is typically not the biological carbon pump, but the physical carbon pump. That has to do with the solubility of CO2. Again, it's a prototype. It shows that we can deal with these levers here. We will add more for mining, for fisheries. We'll add more metrics to show. We'll change the plots to make them a bit more intuitive, but you get a feeling for what we can do, and perhaps also for what we cannot do. There are limits to what you can automate and present. I'll go back to the slides. I hope I will. Let's see. 1 second. I'm hoping you can see this now. Yeah. Okay. No complaints, I'll continue. So this was the demo, proof of concept. Underneath it all, there's a lot happening. It might look simple enough to simulate a single site and a single water column. But underneath it all, it still needs to be able to pick up information from all across the globe in terms of water depth, in terms of meteorology, in terms of tides, in terms of biogeochemistry. And there's a whole range of data sources, essentially state-of-the-art data sources underneath it all. And there's in the end 20 terabytes of data there needed to drive this type of model, where you start from a geographic location and a depth here, go into collecting forcing data, collecting observations from satellites to do some basic validation of the model, then to run the simulations, reference simulations, scenarios, run 5 different biogeochemistries at the same time, here and there, in the end 10 processes in parallel, and then present the whole thing. So there's quite a complex chain there of essentially data flow and programming underneath it all, and it relies on a lot of data there. That's where in part the European digital twin of the ocean comes in. So we're running on top of essentially a cloud-based infrastructure, and Marina will talk much more about that. So I'll just briefly say what we are doing with that. It's a cloud-based infrastructure where applications can come from different people, different projects. Ours comes from OceanICU, so a project essentially originally developed independently of the digital twin delivers this application, and through containerization, if you're into the technical detail, we are able to run on their infrastructure. The key thing here is that it is co-located with very valuable data sets, both the Copernicus marine surface data as well as the EMODnet data, which covers both model outputs and observations, which we can use directly. So technically speaking, we build our containers and we run the containers. There's a whole range of scripts and instructions underneath. And the key thing for us is we are keeping this open. So the tools are open, all the instructions are open. You can go visit different sites and find every single step we do along the way. So it becomes completely traceable. And for everything else about the digital twin, I'll refer to Marina. I'll just say that from the many applications there's at the moment 2 what-if applications listed there if you go to the digital twin, and OceanICU is already there as one of the 2. There's a number of things we would like to work on. One key question that always comes up is how do we deal with uncertainty? You could see some of the model predictions for chlorophyll and CO2. You could see massive spread in model curves, and we're working on reducing that spread because at the moment the models are different and initialized differently. But there will be differences. So we know how to quantify from a technical point of view uncertainty. We can run ensembles of models, provided we can rely on infrastructures such as the digital twin. But that's half the problem. The other half is how do we present the uncertainty to the user? How do we summarize it? How do we visualize it? And that's something we'll develop more in the future. At the moment, we just benefit from the fact that we have these different biogeochemistries in our projects, and we can mix and match them at will. So final slide, what's next? As I said, we'll add more pressures, fishing and mining. We'll need some extra models, in particular for the fish and fisheries, to support that type of run, but we will add that. We'll develop scenarios internally in the projects. We can come up with general levers for mining and fisheries, but we have to translate those to pretty precise parameterizations in models, and that's non-trivial. And we'll work on presentation, ideally through multiple layers. A quick overview of what's going on, as well as a way to click through and see the technical detail. In the long run, what we care about are things like quality control documentation. We'll be as transparent as possible. We'll keep all the model results traceable. And even then, we might have to think carefully about how do we avoid things like misinterpretation of results, cherry picking of results, perhaps even abuse of results here. And finally, I'll just put a promotion in for the next talk by Patrizio. We're working towards fast model emulators based on machine learning. So at the moment, we cannot really do detailed space. Perhaps through machine learning, we can get there. And that will be with machine learning model emulators. That's me. I'll hand over back to Patrizio, I guess.
Thanks, Jorn. I'll just briefly step in here before Patricia starts, just to a common theme here on this for people here listening in is the OceanICU project is leveraging new technological advancements. And I just reminded of that when Jorn showed his model of the Bristol Channel in the UK, because 20 years ago, I was involved in a project modeling the Bristol Channel. And we had to have high, extremely expensive workstations. We had to have racks of hard drives sitting beside that workstation. And it all had to be done inside one room in an environment agency building. Now, through the wonders of modern technology, through the OceanICU, many more people will be able to use what the outputs of OceanICU in the digital support tools. That's just my little plug in there. Thanks. Sorry for that. Over to you, Patricio.
Yeah, I'm here. Can you hear me? I suppose.
Yes. Yeah.
Now, if you go actually back to the previous one, just because Jorn has introduced the topic and actually has showed all the implications of the type of approach that we are following, which is on what he showed in this version 1 and version 2 of these decision support tools. They are basically process-based models. So they are lightweight, but still process-based, meaning that they solve differential equations to reproduce the dynamics that Jorn just showed. Here, in this version 3, we are trying to follow a different approach where we still use the information coming from this process-based model, but we go towards a statistical representation of this process-based model. These are what are the emulators or a surrogate model. So it's basically a reduced complexity climate model in this case that can run much faster, faster than the lightweight models that Jorn shown before, but retaining the accuracy on the processes that is resolving. What's the advantage of that? Because you can explore some of the scenarios that Jorn demonstrated before much faster. And that's the idea behind it. And also some ideas about what type of perturbation we can have on these methods. But the topic of deep learning and Earth system science has been around now for a few years. I think the main motivation is because we live in an era of big data, even in the ocean, although, I mean, the ocean is huge, as you know, but the amount of information that we are getting daily is also quite remarkable. I think rough calculation in terms of daily satellite or Earth system observations coming into Copernicus is about like 450 terabytes or something like that. If you think about also the inner part of the ocean, which is the Argo floats, maybe we have 4,000 of them making a profile every 10 days. That's about 15,000 profiles with millions of points that are recorded during these profiles. So we have actually quite a lot of data. They are not harmonized. They are scattered all around. They are not in the places that we would like. But maybe we can use deep learning to extract knowledge out of this information. That's basically what this paper that was published, I think, a few years back in 2019, was a review about how we can actually leverage deep learning methods to help Earth system science. And they sketched different methods because you can work out data assimilation procedures with machine learning to optimize actually the input that you have and the parameters that you have to fit with the observations that you might have on specific variables. And there are groups working on that. You can also think about hybrid modeling, which is also quite interesting. So replacing places in the model or in this process-based model, phenomena that you are not able to resolve or not very good at resolving. And you can try to make a statistical or a closure of the problem, making statistical models to represent them. This is routinely done in cloud, for example, formation and rain in atmospheric science. In a way, it's also similar to what we do in ocean science for a turbulence closure model, although a bit different. But hybrid modeling is also one of these hot topics that is out there. What we focus on, of course, is the use of the emulators for decision support tools. Next one slide. Yeah. Emulators in terms of Earth system science and climate prediction is not new. Indeed, I mean, they have been used over the years. But the emulators that have been used so far, they are very simple statistical representation, pretty much like regressions. Still, they actually have quite a lot of predictive power. These are extracted directly from the IPCC report, the latest one. And well, you can quickly see that these are the different kind of model output from the CMP6 models. They have an envelope of uncertainties, and if you actually calibrate a set of emulators, and there are several that are listed there, you can actually obtain very accurate predictions of what the ensemble should produce. Indeed, this is the method actually that is used to produce ensemble of the global mean surface air temperature, which is what is showed here. So we know that actually works, and there is actually quite high confidence that at least for air temperature, we can actually get quite far with the use of emulators. Next. The question is how much this tool can be used in the ocean. And there are now very recently few examples out there, mostly pushed by large organizations or companies like NVIDIA or Google and Amazon. We can go back about the collaborations between science and industry in this specific context, because I think it's interesting. But here, basically, it's one of the first attempt to model, for example, sea surface temperature in the El Niño region. And they show that actually after some training, they have a coupled emulator for atmospheric and ocean dynamics that can actually accurately reproduce the dynamic of El Niño and La Niña over multiple years. What is showed there is the anomaly in SST, indeed. The red is coming from this ensemble of emulators, and we can go back to the technicalities, while the purple line is the process-based type of model. So actually, the emulator, it seems to be better in predicting some of this, although it is basically trained with also the model output from the GFDL plus additional observations. This is based in NVIDIA, a sponsor type, and actually they are launching a much bigger program, which is called Earth-2, where they intend to have, let's say, a digital representation of Earth, which seems to be quite interesting. Following this, in our approach is actually to focus on the carbon cycle, because that's what OceanICU is contributing also in terms of new knowledge and new processes. And we think to actually be able to build emulators to simulate or to focus on the carbon export in the ocean. Next, please. Yeah, what's the challenge in very kind of general terms? I don't know how much deep we want to go with this one, but you can think about the problem being that we have a system, in this case represented by Y, that will respond to some perturbation, in this case represented by zeta. This perturbation can be a specific point at a specific time, and the response of the system will depend on what we know as a kernel function. Kernel function is basically a translation of this perturbation into an effect on the system. And we can think about different types of kernels, some of them very simple, like exponential decay in time and space or things like that. But what is interesting is that this kernel function, or in other contexts, it's probably called like a manifold in a very complex system like the Earth system, can actually be discovered by machine learning approaches. And there is a paper very recently published, which is called Deep Green, where they actually do exactly that. It's for a specific class of phenomena, these boundary value problems, which indeed actually might fit quite well with climate models because they are boundary value problems. So you change the boundary conditions and you have different dynamics in the system, considering the Earth as an isolated system. We have been experimenting a little bit of that in OceanICU. We are not yet at the how to say, at the status that we can show the results, but I think it's a very promising avenue for modeling and for building some of these emulators. Next, please. One additional element that Jorn also mentioned briefly is that we want to exploit better the spatial dynamic as well as the temporal one and the changes in boundary conditions. And it seems that there is a good candidate architecture in terms of a deep learning architecture to do that, which is called graph neural networks. They have been used, for example, by Google in what is called GraphCast, which is the new machine or deep learning approach that they have for a weather forecast. It is based on GNN architecture and actually shows that the performances can be much better than the process-based models. We don't expect maybe the same for climate models, but we think that GNN is something to look at in terms of building emulators for Earth system. So GNN's very successful modeling Earth system processes, but also have been used and actually developed initially for modeling road traffic, for example, where actually they have very good performances. I think at this point I have a small animation of what GNNs can actually do. If you go to the next slide, and if you start, before you start, to the left, the ground truth there is coming from what is called direct numerical simulations, so solving directly the Navier-Stokes equations and creating, these interactions between a fluid and the boundary or the walls there. While on the right, you have a GNN-trained deep learning model to reproduce some of these dynamics. So if you start the video now, you can actually see, of course, just eyeball type of assessment, that the model is actually quite good in reproducing some of these dynamics. But most interesting is that if you change some of the conditions, once the model is trained, if you change some of the conditions, for example, you change the shape of these walls, or you change the type of interactions that the water molecules will have with the wall, the statistical model will be able to capture that. So it basically means that it is able to capture some essential physics of the problem, which allows basically to extrapolate out of the training set that you have used to train the model. Next, please. Yeah, so what's the strategy in OceanICU? We know that, for example, the CMP6, which correspond to something like 30 petabytes of data, they are stored on the cloud, which is actually quite convenient because it's very close to quite high computing power that actually we need to train this stuff. Once they are trained, they run quite fast, but to train them, it takes a lot of resources. We want to use those output models basically to start training some of our models and start developing some scenarios. Next, yeah. And we think that, we will try to exploit both this GNN architecture and maybe RNN, which is a recursive neural network type of approach to capture the time correlation, but also try to constrain some of the quantities in the statistical model based on physics. So some mass balance I could think of, or energy balance, which we can exploit to shape this loss function in a better way. And actually, Jorna showed a set of model, and we have in mind specific models within OceanICU where to actually start mimicking what the process-based model are doing. Next, please. But we didn't start yet to go full speed on this. And I'm not the most expert on these tools. We have been playing with machine learning approaches in different contexts even for emulation in the Black Sea, for example. But we are just starting. The strategy will be to actually recruit a postdoc, and I want to use the forum here also to advertise that. The position will be available, I think, in a couple of weeks on the DTU website. And we target a postdoc because we want to have someone already experienced with these emulator strategies. As I mentioned, then we will move with the CMP6 model output that are stored on the cloud. Maybe the use of the EDITO infrastructure here can help to kind of fill the gap between, well, the resources, computing resources we have available and what we will need to train these models. I mentioned already the use of GNN, and of course, we are waiting to receive also this improved parameterization of the biological carbon pump that will emerge from the OceanICU consortium in the other work packages, and try to actually have those included in the statistical or in the emulator that we will build as well. We plan to have something ready by 2026. Well, keep tuned and keep up with the updates that we will have. Thank you.
Thank you very much, Patricio. Next, we're going to have Marina, and I just want to add some context here. Marina and myself worked together on the EDITO project. I work for Seascape Belgium, and we provide the EMODnet data services for the European Commission. Marina, this company provides the Copernicus marine services for the European Commission. So Copernicus Marine and EMODnet are working together to make our data products more accessible and faster and more scalable for projects like OceanICU via the EDITO platform. But Marina will be able to tell you more about it now. So over to you, Marina.
Thank you very much, Connor, and thanks for your nice introduction. So we can go directly to the next slide. And as already been said, so what we are aiming to do with the European Digital Twin of the Ocean platform is to provide a unique and easy access to marine data assets. And we are starting with the Copernicus and EMODnet one that have been made available. They are already available via EDITO, and then this will be extended to many more. And at the core of the platform, there is the source of information that we can get from these marine assets, together with tools and models that can allow you to play with the data, or also to develop your tools and your models in order that to have information on physics, biochemistry, marine species ecosystem, socioecology, so that we can make ocean knowledge that is easily accessible and available for different communities that can go from scientists and policymakers to citizens that can have access to all of this information. Just to give you a little bit of context, so the European initiative on the digital twins has been launched during the One Ocean Summer in February 2022 as a main element of the digital ocean knowledge system under the EU mission Restore Our Ocean. And since the very beginning, they set a very ambitious goal that was to have in less than 2 years a digital twin operational. And so it means now. And we have launched, as has been already mentioned, I think in the very beginning by Connor, at the Digital Ocean Forum last June, the prototype of this platform that is already available. And we can now go to the next slide. So what is offering? So it's offering the opportunity to explore. That means that you can go there and see everything that is available in terms of data, in terms of models and tools. Then you can create, so you can add your data, create your tools, generate new data and new application, make your what-if scenario, and you can also contribute to the platform. As OceanICU did, and OceanICU, we are really happy that you have been one of our first beta testers that has successfully contributed to the platform. And so next slide, please. So this is just a simple overview of the platform. On the top right, you can see the URL for reaching the platform. And there is a set of tutorials that are available for helping you to understand what you can do. There is a model lab that is where you can play with the tools. And there is also the part where you can explore all the oceanographic data, so where you have a viewer and you can go through the catalog of the information that are there. Next slide, please. This is a very, let's say, a simple sketch of the architecture of the EDITO platform, where you can see the different components in terms of data lake, engine, and service that are offered, and the web user interface. But what I want to point out with this slide is that it relies on a set of standards and APIs, and this is for promoting interoperability and enhance the use of the platform, because we can go to the next slide, please. Because what is really important is that EDITO has this, let's say, mission to develop the platform, but the platform per se doesn't mean much, but we need the contribution and the co-construction of the content of the platform with all the projects like your projects. And so we do this through a sequence of events that are the DigitalOcean Forum that are happening on a yearly basis. And hopefully we will do also in future with more frequent events, so that we can really reach out all the community that can benefit from EDITO and can contribute and create their own tools in EDITO. And I like to conclude with citing John Bell, saying that this is why we got to the moon and back. It is because people were inspired and people felt part of it. And I really wish that you can feel part of EDITO and you are inspired by EDITO, so that we can contribute all together to build ocean marine knowledge for the European digital ocean. Thank you for your attention.
Thank you, Marina. I believe, thank you very much for that interesting presentation. I do believe I have a slide I have to go over here on a questionnaire. So there is a questionnaire that my colleagues in OceanICU are requesting that people try and fill in. You can get to it by the QR code at the bottom, and it will be very useful or very helpful to us all in our work if you could take the time to participate. So for this, can we go to the next slide there, please? Questions and answers, and I asked my colleagues to switch back on their cameras. So what you saw here was the incredible work of our colleagues Jorn and Patricio, supported by the new initiative from the Commission about how to deal with the problem of big data and cloud computing in her research context. And this was very much on the minds of our colleagues in EMODnet and Copernicus Marine. So I don't want to go too much into that, but just to try and put it into context for you. So does anybody here have questions for the people doing the real work, which is Jorn and Patricio? And I noticed from the chat there were no questions, which means that you did a fantastic presentation. Okay, so if I don't see any questions there, does anyone any questions for Marina on the EDITO platform? And I ask if you have questions to put them in the chat. And I don't see any there either. So I think then we can wrap this up and finish off. We had quite a great turnout. Thank you all for taking part today. If for some reason you weren't able to get, oh, I have one message coming through. For some reason you weren't able to ask the question you wanted, please feel free to reach out to us. We'll redirect the question to the panelists. And I hope you take away and see from this, you can see what amazing work has been done here and how new technologies are leveraging new investigations and hopefully lead to new solutions. Thank you very much for taking part.